Two-dimensional vectors, Level 1. In the following series of videos, we're going to cover vectors both geometrically and algebraically. In general, vectors are used to represent lines and planes in geometry, and are also used to represent quantities such as force and velocity in physics. Many quantities in geometry and physics, such as length, area, volume, temperature, mass, and time, can be described by a single real number that is scaled to an appropriate unit of measurement, like grams, which is a unit of mass. These quantities are called scalar quantities, and the real number associated with each quantity is called a scalar. Quantities such as force, displacement, velocity, and acceleration involve both a magnitude and a direction, and cannot be characterized completely by a single real number. A convenient way to represent these types of quantities is by using vectors. A vector is essentially a directed line segment, represented by an arrow. The directed line segment is constructed by an initial point P, also known as a tail, and a terminal point Q, also known as a tip or head of the vector. We can denote these vectors by writing the letters of the initial point, in this case P, and the terminal point, in this case Q, and then we draw an arrow on top of the letters as follows. Similar to a line segment from geometry, vectors have a definite measurable length. The length of a vector is referred to as the magnitude of the vector, and is denoted as follows, using the absolute value symbol, or by using double vertical bars as follows. In these videos, I will use the double vertical bars to denote the magnitude of a vector. Some textbooks will use the absolute value symbol. Unfortunately, this notation can be misleading. Many students think that they need to find the absolute value rather than the magnitude of a vector. Because of this potential confusion, I will use the double vertical bars to denote the magnitude of a vector. Next, let's talk about equivalent vectors. In general, directed line segments that have the same length, magnitude, and direction are said to be equivalent. For example, the following two vectors are equivalent because the length or magnitude of each vector is the same, and they are both pointing in the same direction. On the other hand, the following two vectors are not equivalent vectors, because one vector is longer than the second vector. In other words, the first vector has a greater magnitude compared to the second vector. Notice that both vectors are pointing in the same direction. Although they share this common characteristic, they are not considered to be equivalent vectors, because both the magnitude and direction need to be the same. Similarly, the following two vectors are also not equivalent. Notice that they have the same length, but each vector is pointing in a different direction. In this scenario, only one of the two requirements for vector equivalence is satisfied. As a final example, the following two vectors are not equivalent, since both vectors have distinct magnitudes and directions. In this case, none of the two requirements for vector equivalency is satisfied. Keep in mind that both the magnitude and direction need to be the same for two vectors to be considered equivalent. Another notation that is used to denote vectors is by assigning a lowercase boldface letter such as U, V, and W. In practice, it is pretty tricky to write boldface letters on paper. So, an alternative way to denote vectors is by using a lowercase letter with an arrow on top, similar to the way we denoted rays in geometry class. This way, we can denote vector PQ as vector V. If we wanted to denote that two vectors are equivalent or equal, all we need to do is place an equal sign between the two symbols as follows. Vector V equals vector U. Lastly, we can denote a special vector that has no specific direction. This vector is called the zero vector, and is denoted as follows. This vector has a length of 0, hence the zero vector. It is usually represented as a single point you can think of this vector as having the same initial and terminal point. The direction of 0 vectors can technically point in any direction, but we will not bother assigning a specific direction. Let's go over a couple of examples. Name all equivalent vectors in the parallelogram shown. Alright, recall that 2 vectors are equivalent if they have the same direction and magnitude, but they don't necessarily need to be at the same location. Since we're told that this is a parallelogram, both pairs of opposite sides are congruent and parallel. Also, the diagonals of the parallelogram bisect each other. With this information at hand, we can start naming all the equivalent vectors. Recall that vectors are direction sensitive, so we need to denote the initial or tail first, followed by the head or terminal point. Vector AB is equivalent to vector DC, since both vectors have the same length. They are parallel and both point in the same direction. In the same manner, vector AD and vector BC are also equivalent, since they have the same magnitude and direction. Now, let's take a look at the diagonals. We know from elementary geometry that the diagonals of a parallelogram bisect each other. This means that vector DE and vector EB have the same magnitude or length. They also lie along the same line and point in the same direction. Notice that all requirements for vector equivalency are met. Hence, these vectors are equivalent. Finally, vector AE and vector EC are also equivalent because they have the same magnitude and direction. Again, because of the geometric properties of parallelograms. Alright, let's go over the final example. Name all the equivalent vectors in the figure shown. Quadrilateral ABCD is congruent to quadrilateral CEGF. Alright, recall that when 2 figures are congruent, corresponding angles and corresponding sides of the figure have the same measurement. This means that all of these vectors have the same length, or magnitude. Also, since right vertical angles form at point C, the corresponding sides of the quadrilaterals are also parallel to one another. With this information, we can conclude that vector BA is equivalent to vector GF. Vector CB is equivalent to vector GE. Vector DC is equivalent to vector CE. And vector AD is equivalent to vector CF. Keep in mind that both the magnitude and direction of the vectors need to be the same. Okay, in our next video, we will start learning how to describe vectors in a 2-dimensional coordinate system.